image processing. In the last class, we have seen the interpolation and resampling operation of images, and we have seen different applications of the interpolation and resampling operations. So, while we have talked about the interpolation and resampling, we have seen that it is the B-spline functions or B-spline interpolation functions of different orders which are mainly used for image interpolation purpose. And before this interpolation, we have also talked about the basic transformation operations, and the transformation operations that we have discussed, those were mainly in the class of geometric transformations. That is, we have talked about the transformation like translation, we have talked about rotation, we have talked about scaling, and we have seen that these are the kind of transformations which are mainly used for coordinate translation. That is, given a point in one coordinate system, we can translate the point or we can represent the point in another coordinate system, where the second coordinate system may be a translated or rotated version of the first coordinate system. We have also talked about another type of transformation, which is perspective transformation, and this perspective transformation is mainly used to find out or to map a point in a three-dimensional world coordinate system to a two-dimensional plane, where this two-dimensional plane is the imaging plane. So, there our purpose was that given a point or the 3D coordinates of a point in a three-dimensional coordinate system, what will be the coordinate of that point on the image plane when it is imaged by a camera. In today's lecture, we will talk about another kind of transformation, which we call as image transformation. So, we will talk about or we will explain the different image transformation operations. Now, before coming to specific transformation operations like say Fourier transform or discrete cosine transform or say discrete cosine transform, before we come to such specific transformations, we will first talk about a unitary transformation, which is a class of transformations or class of unitary transformations, and all the different sort of transformations, that is whether it is discrete Fourier transform or discrete cosine transform or Hadamard transform, all these different transforms are different cases of this class of unitary transformations. Then when we talk about this unitary transformation, we will also explain what is an orthogonal and orthonormal basis function. So, we will see that what is known as an orthogonal basis function, what is also known as a orthonormal basis function. We will also explain how an arbitrary one-dimensional signal can be represented by series summation of orthogonal basis vectors, and we will also explain how an arbitrary image can be represented by a series summation of orthonormal basis images. Now, firstly, let us see that what is the image transformation. You find that in this case we have shown a diagram where the input is an image, and after the image is transformed, we get another image. So, if the size of the input image is n by n, say it is having n number of rows and n number of columns, the transformed image is also of same size, that is of size n by n. And given this transformed image, if we perform the inverse transformation, we get back the original image, that is image of size n by n. Now, if given an image, by applying transformation, we are transforming that to another image of same size, and doing the inverse transformation operation, we get back the original image, then the question naturally comes that what is the use of this transformation. And here you find that after transformation, the second image of same size n by n that we get, that is called the transform coefficient matrix. So, the natural question that arises in this case, that if by transformation I am going to another image and by using inverse transformation I get back the original image, then why do we go for this transformation at all? Now, you will find, and we will also see in our subsequent lectures, that this kind of transformation has got a number of very important applications. One of the application is for pre-processing. In case of image pre-processing of the images, if the image contains noise, then you find, or you know, that contamination of noise gives rise to high frequency components in the image. So, if by using some sort of unitary transformation, we can find out what are the frequency components in the image, then from these frequency coefficients, if we can suppress the high frequency components, then after suppressing the high frequency components, the modified coefficient matrix that you get, if you take the inverse transform of that modified coefficient matrix, then the original image or the reconstructed image that we get, that is a filtered image. So, filtering is very important application where these image transformation techniques can be applied. The other kind of pre-processing techniques we will also see later on, that it is also very useful for image enhancement operation. So, for example, if we have an image which is very blurred, that is the contrast of the image is very poor, then again in the transformation domain or using the transform coefficients, we can do certain operations by which we can enhance the contrast of the image. So, that is what is known as enhancement operation. We will also see that these image transformation operations are very useful for data compression. So, if I have to transmit an image or if I have to store the image on a hard disk, then you can easily think that if I have an image of size 512 by 512 pixels, and if it is a black and white image, every pixel contains 8 bits. If it is a color image, every pixel contains normally 24 bits. So, storing an image, a colored image of size 500 and 512 by 512 pixel size takes huge amount of disk space. So, if by some operation I can compress the space or I can reduce the space required to store the same image, then obviously on a limited disk space I can store more number of images. Similar is the case if I go for transmission of the image or transmission of image sequences or video. In that case, the bandwidth of the channel over which this image or the video has to be transmitted is a bottleneck, which forces us that we must employ some data compression techniques, so that the bandwidth requirement for the transmission of the image or the transmission of the video will be reduced. And we will also see later on that these image transformation techniques is the first step in most of the data compression or image or video compression techniques. These transformation techniques are also very useful for feature extraction operation. By features, I mean that in the images, if I am interested to find out the edges or I am interested to find out the corners of certain shapes, then these transformation techniques, or if I work in the transformation domain, then finding out the edges or finding out the corners of certain objects, that also becomes very convenient. So, these are some of the applications where this image transformation techniques can be used. So, apparently we have seen that by image transformation I just transform an original image to another image, and by inverse transformation that transformed image can be retransformed to the original image. So, the application of this image transformation operation can be like this, and here I have cited only few of the applications. We will see later that applications of these image transformations are much more than what I have listed here. Now, what is actually done by image transformation? By image transformation, what we do is we try to represent a given image as a series summation of a set of unitary matrices. Now, what is an unitary matrix? A matrix A is said to be an unitary matrix if A inverse or inverse of A is equal to A star transpose, where A star is the complex conjugate of A. So, a matrix A will be called an unitary matrix if the inverse of the matrix is same as, first you take the conjugate of the matrix A, then take its transpose. So, A inverse will be equal to A star transpose, where A star is the complex conjugate of the matrix A, that is complex conjugate of each and every element of matrix A. And these unitary matrices we will call as the basis images. So, the purpose of this image transformation operation is to represent any arbitrary image as a series summation of such unitary matrices or series summation of such basis images. Now, to start with, I will first try to explain with the help of one dimensional signal. So, let us take an arbitrary one dimensional signal. Say I take a signal, say x t. So, I take an arbitrary signal x t, and you see that this is a function of t. So, this x t, the nature of x t can be anything. Say let us take that I have a signal like this x t, which is a function of t. Now, this arbitrary signal x t can be represented as a series summation of a set of orthogonal basis functions. So, I am just taking this as an example for one dimensional signal, and later on we will extend to two dimension, that is for the images. So, this arbitrary signal, this one dimensional signal x t, we can represent by the series summation of a set of orthogonal basis functions. Now, the question is, what is orthogonal? By orthogonal, I mean that if I consider a set of real valued continuous functions. So, I consider a set of real valued continuous functions, say a n t, which is equal to set say a 0 t, a 1 t, and so on. Okay. So, this is a set of real valued continuous functions, and this set of real valued continuous functions is said to be orthogonal over an interval say t 0 to t 0 plus t. So, I define that this set of continuous real valued functions will be orthogonal over an interval t 0 to t 0 plus capital T if I take the integration of function say a m t into a n t dt and take the integration of this over the interval capital T, then this integral will be equal to some constant k if m is equal to n, and this will be equal to 0 if m is not equal to n. So, I take two functions a m t and a n t, take the product and integrate the product over interval capital T. So, if this integration is equal to some constant say k when m is equal to n, and this is equal to 0 whenever m is not equal to n. So, if this is true for this set of real valued continuous functions, then this set of real valued continuous functions form an orthogonal set of basis functions. And if the value of this constant k is equal to 1, so if the value of this constant k is equal to 1, then we say that the set is orthonormal. Okay. So, an orthogonal basis function, as we have defined, this non-zero constant k, if this is equal to 1, then we say that it is a orthonormal set of basis functions. Let us just take an example that what do we mean by this. Suppose we take a set like this. So, sin omega t, sin twice omega t and sin 3 omega t. So, this is my set of functions a n t. Okay. Now, if I plot sin omega t over interval t equal to 0 to capital T. Okay. So, this will be like this, and where omega is equal to 2 pi by capital T. So, capital T is the period of this sinusoidal wave. Then if I plot this sin omega t, you will find that sin omega t in the period 0 to capital T is something like this. So, this is t, this is sin omega t, and this is the time period capital T. If I plot twice omega t over this same diagram, sin of twice omega t will be something like this. Okay. So, this is sin of this is sin of twice omega t. Now, if I take the product of sin omega t and sin twice omega t in the interval 0 to capital T, the product will appear something like this. So, you find that in this particular region, both sin twice omega t and sin omega t, they are positive. So, the product will be of this form. In this region, sin omega t is positive, but sin twice omega t is negative. So, the product will be of this form. In this particular region, sin twice omega t is positive, whereas sin omega t is negative. So, the product is going to be like this. This will be of this form, and in this particular region, both sin omega t and sin twice omega t, they are negative. So, the product is going to be positive. So, it will be of this form. Now, if I integrate this, so if I integrate sin of omega t into sin of twice omega t dt over the interval 0 to capital T, this integral is nothing but the area covered by this curve. And if you take this area, you will find that the positive half will be cancelled by the negative half, and this product will come out to be 0. This integration will come out to be 0. Similar is the case if I multiply sin omega t with sin 3 omega t and take the integration. Similar will also be the case if I multiply sin twice omega t with sin 3 omega t and take the integration. So, this particular set, that is sin omega t, sin twice omega t and sin 3 omega t, this particular set is the set of orthogonal basis functions. Now, suppose we have an arbitrary real valued function x t, and this function x t is we consider within the region t 0 less than or equal to t less than or equal to t 0 plus capital T. Now, this function x t can be represented by as a series summation. So, we can write x t as summation C n a n t. So, you remember that a n t is the set of orthogonal basis functions. So, we represent x t as a series summation. So, x t equal to sum of C n a n t, where n varies from 0 to infinity. Then this term C n is called the nth coefficient of expansion. This is called nth coefficient of expansion. Now, the problem is how do we find out or how do we calculate the value of C n. To calculate the value of C n, what we can do is we can multiply both the left hand side and the right hand side by another function from the set of orthogonal basis functions. So, we multiply both sides by function say a m t and take the integration from t equal to 0 to capital T, or take the integration over the interval capital T. So, what we get is we get an integration of this form x t a m t dt integral over capital T. This will be equal to again integral over capital T, and this integral of C n a n t into a m t, because we are multiplying both the left hand side and the right hand side by the function a m t dt, and you take the integral over the interval capital T. Now, if I expand this, you find that if I expand this, this will be of the form C 0 integration over capital T a 0 t into a m t dt plus C 1 integration over the same interval capital T a 1 t into a m t dt plus it will continue like this. We will have one term say C m integral over t a m t into a m t dt plus some more integration terms. Now, as per the definition of the orthogonality that we have said, that a integral of a n t into a m t into dt, that will be equal to some constant k if and only if m is equal to n, and this integral will vanish for all the cases wherever m is not equal to n. So, by using that formula of orthogonality, what we get in this case is we simply get integral x t into a m t dt, this integral over capital T, this will be simply equal to constant k times C m, because the right hand side of this integration that you have said, this right hand side all these terms will be equal to 0, only for this term a m t into a m t dt the value will be equal to k. So, what we get here is integration x t a m t dt is equal to the constant k times C m. So, from this we can easily calculate that the mth coefficient C m will be given by 1 upon k integration x t amt into dt, where you take the integration over the interval capital T. And obviously, you can find out that if this set is an orthonormal set, not an orthogonal set, in that case value of k is equal to 1. So, we can easily get the mth coefficient C m to be x t c a m t dt, integrate this over the interval t. So, the value of term k will be equal to 1. So, this is how we can get the mth coefficient of expansion of any arbitrary function x t, right. And this computation can be done if the set of basis functions that we are taking, that is the set A n t, is an orthogonal basis function. Now, the set of orthogonal basis functions A n t is said to be complete. We say that this orthogonal basis function is complete if this is complete or closed if one of the two conditions hold. The first condition is there is no signal, say x t, with integral x square t dt over the interval capital T less than infinity. So, this means the signal with finite energy. So, there does not exist any signal x t with x square t dt less than infinity, such that integral x t a n t dt is equal to 0. This integration has to be taken over the interval capital T for n equal to 0, 1 and so on. And the second condition is that for any piecewise continuous signal x t, so x t is piecewise continuous, and with the same condition of finite energy, that is x square t dt, integral over capital T must be less than infinity. And if there exists an epsilon greater than 0, however small this epsilon is, there exists an n and a finite expansion such that x hat t is equal to C n a n t. Now, n varies from 0 to capital N minus 1, such that integral x t minus x hat t square dt taken over the same interval capital T must be less than epsilon. So, this says that for a piecewise continuous function x t having finite energy, there must be an epsilon which is greater than 0, but very small, and there must be some constant capital N, such that if we can have an expansion that x hat t is equal to summation of C n a n t. Now, this n varies from 0 to capital N minus 1, for which this term x t minus x hat t square dt over integral over capital T, this is less than epsilon. So, you find that this x t is the original signal x t, and x hat t, earlier case we have seen that if we go for infinite expansion, then this x t can be represented exactly. Now, what we are doing is we are going for a truncated expansion. We are not going to take all the infinite number of terms, but we are going to take only capital N number of terms. So, obviously, this x t, it is not being represented exactly, but what we are going to have is an approximate expansion. And if x t is of finite energy, that is integral of x square t dt integration over capital T is less than infinite, then we can say that there must be a finite n, capital N, the number of terms for which the error of the reconstructed signal. So, this x t minus x hat t square dt, this is nothing but the energy of the error signal or the error that is introduced because of this truncation, which must be limited. It must be less than or equal to epsilon, where epsilon is a very, very positive small value. So, we say that the set of orthogonal basis functions a n t is complete or closed if one of these conditions hold, at least one of these conditions hold, that is the first condition or the second condition. So, this says that when we have a complete orthogonal function, then this complete orthogonal function expansion enables representation of x t by a finite set of coefficients, where the finite set of coefficients are C 0, C 1 like this up to C n minus 1. So, this is the finite set of coefficients. So, if we have a complete orthogonal function, set of orthogonal functions, then using this complete set of orthogonal functions, we can go for a finite expansion of a signal x t using the finite number of expansion coefficients C 0, C 1 up to C n minus 1, as is shown here. So, I have a finite set of expansion coefficients. So, from this discussion, what we have seen is that an arbitrary continuous signal x t can be represented by the series summation of a set of orthogonal basis functions, and this series expansion is given as x t is equal to C n a n t, where n varies from 0 to infinity if I go for infinite expansion, or this can also be represented, as we have seen, by finite expansion, finite series expansion. In this case, this will be represented by C n a n t, where n will now vary from 0 to n capital N minus 1. So, this is x hat t. So, obviously, we are going for an approximate representation of x t, not a complete expansion, not the exact representation of x t. So, this is the case that we have for continuous signals x t. But in our case, we are not dealing with the continuous signals, but we are dealing with the discrete signals. So, in case of discrete signals, what we have is a set of samples or a series of samples. So, the series of samples can be represented by, say, u n, where 0 less than or equal to n less than or equal to capital N minus 1. So, we have a series of discrete samples u n. So, in this case, we have capital N number of samples. So, obviously, you can see that this is a one dimensional sequence of samples, and because it is one dimensional sequence of samples and the sample size is capital N, that is we have capital N number of samples. So, I can represent this set of samples by a vector, say u, of dimension capital N. So, I am representing this by a vector u of dimension capital N. And for transformation, what I do is I pre-multiply this vector u by a unitary matrix A of dimension n by n. So, given this vector u, if I pre-multiply this with a unitary matrix capital A, where the dimension of this unitary matrix is n by n. So, you find that this u is a vector of dimension n, and I have a matrix, a unitary matrix of dimension n by n. So, this multiplication results in another vector v. So, this vector v we call as a transformed vector or transformation vector. This is transformed vector, and this unitary matrix A is called the transformation matrix. So, what I have done is I have taken an n dimensional vector u, pre-multiplied that n dimensional vector u by a unitary matrix of dimension n by n. So, after multiplication I got again an n dimensional vector v. Now, so by matrix equation, this is v equal to a times u. If I expand this, so now what I do is I expand this matrix equation. So, if I expand this matrix equation, this can be represented as a series summation, which will be given by v k is equal to a k n into u n, where n varies from 0 to capital N minus 1, and this has to be computed for k equal to 0, 1 up to n minus 1. So, I get all the n elements of the vector v k. Now, if A is an unitary matrix, then from vector v I can also get back our original vector u. So, for doing that, what we will do is we will pre-multiply v by A inverse. So, this should give me the original vector u, and this A inverse v, because this is an unitary matrix, will be nothing but A conjugate transpose v. And if I represent this same equation in the form of a series summation, this will come out to be u n is equal to A star k n times v k, where k will now vary from 0 to n minus 1, and this has to be computed for all values of n varying from 0, 1 up to n minus 1. Now, you find that what is this A star k n? Now, if I represent this A k n, or if I expand this matrix A k n, this is of the form A 1 1 or A 0 1, A 0 2, A 0 3, like this, A 0 n, A 1 0, sorry, this is A 0 0, A 0 1, A 0 2 up to A 0 n. This will be A 1 0, A 1 1. So, it will go like this, and finally, I will have A k 0, A k 1, like this. I will have A k n. Now, find that in this expression we are multiplying A k n by V k, or A k n star, which is the conjugate of A k n into V k. Now, this A k n star is nothing but the column vector of matrix A star. So, if I have this matrix A, this A k n star is nothing but a column vector of matrix A star. So, these column vectors or column vectors of matrix A star transpose. So, these column vectors or A k n star, A k n star, these column vectors are actually called the basis vectors of the matrix A. And you remember, this matrix A is an unitary matrix. And here what we have done is the sequence of samples u n or vector u n has been represented, because we have represented a n u n as summation of a star k n into v k for k equal to 0 to n minus 1. So, this vector u n has been represented as a series summation of a set of basis vectors. Now, if this basis vector has to be orthogonal or orthonormal, then what is the property that it has to follow? So, if we have a set of basis vectors, and in this case we have said that the columns of A star transpose, this forms the set of basis vectors. So, if I take any two columns and take the dot product of those two columns, the dot product is going to be non-zero. The dot product is going to be 0. And if I take the dot product of the column with itself, this dot product is going to be non-zero. So, if I take a column, say a column I, and take the dot product of A I with A I, or I take two columns A I and A j and take the dot product of these two columns. So, this dot product will be equal to some constant k whenever I is equal to j, and this will be equal to 0 whenever I is not equal to j. So, if this property is followed, then the matrix A will be an unitary matrix. So, in this case we have represented the vector v or vector u by a series summation of a set of basis vectors. So, this is what we have got in case of a one dimensional signal or an one dimensional vector u. Now, we are talking about image transformation. So, in our case our interest is on image transformations. Now, the same concept of representing a vector as a series summation of a set of basis vectors can also be extended in case of an image. So, in case of an image, the vector u that we have defined in the earlier case, now it will be a two dimensional matrix. So, u instead of being a vector, now it will be a two dimensional matrix, and we represent this by u m n, where m and n are row and column indices, where 0 is less than or equal to m n and less than or equal to n minus 1. So, I see that we are considering an image of dimension capital N by capital N. Now, transformation on this image can be represented as V k L will be equal to, again we take the series summation A k L m n into u m n, where m and n vary from 0 to capital N minus 1. Okay. So, here you find that A k L is a matrix again of dimension capital N by capital N, but in this case the matrix itself has an index k L, and this computation V k L has to be done for 0 less than or equal to k L less than or equal to capital N minus 1. So, this clearly shows that the matrix that we are taking, this is of dimension capital N by capital N, and not only that, we have capital N into capital N, that is n square, capital N square number of such matrices or such unitary matrices. So, this A k L m n, because k and L both of them take the values from 0 to capital N minus 1. So, I have capital N square number of unitary matrices, and from this V k L, which is in this case the transformation matrix, I can get back this original matrix u m n by applying the inverse transformation. So, in this case u m n will be equal to again double summation A star k dash L dash into V A star k L into let me rewrite this. We will have U m n will be given by double summation A star k L m n V k L, where k L varies from 0 to n minus 1, and this has to be computed for 0 less than or equal to m n less than or equal to capital N minus 1. So, find that by extending the concept of series expansion of one dimensional vectors to two dimension, we can represent an image as a series summation of basis unitary matrices. So, in this case all of A k L or A star all of A k L m n will be the unitary matrices. Now, what is the orthogonality property? What is meant by orthogonality property in case of the matrix? The orthogonality property says that for this matrix A, it says that A k L m n into A k dash L dash m n. If I take this summation for m n equal to 0 to capital N minus 1, this will be equal to a Kronecker delta function of k minus k dash and L minus L dash. So, it says that this functional value will be equal to 1 whenever k is equal to k dash and L equal to L dash. In all other cases, this summation will be 0. And the completeness says that if I take the summation A k L m n into A k L, sorry, this should be A k dash L dash star. So, A k L star m dash n dash, summation is taken over k and L equal to 0 to capital N minus 1. This will be equal to Kronecker delta function m minus m dash and n minus n dash. So, it says that this summation will be equal to 1 whenever m is equal to n dash and n is equal to n dash. So, the matrix, by applying this kind of transformation, the matrix V, which we get, which is nothing but set of V k L, this is what is the transformed matrix or the transformation coefficients. So, this is also called the transform coefficients. So, we find that in this particular case, any arbitrary image is represented by a series summation of a set of basis images or set of unitary matrices. Now, if we truncate the summation, so in this case what we get is we get the set of coefficients and the coefficient size is same as the original image size, that is, if we have n by n image, our coefficient matrix will also be of n by n. Now, instead, while doing the inverse transformation, if I do not consider all the coefficient matrices, I consider a subset of it. In that case, what we are going to get is an approximate reconstructed image, and it can be shown that this approximate reconstructed image will will have an error, a limited error, if the basis matrices that we are considering, the set of basis matrices or set of basis images, that is complete. So, this error will be minimized if the basis images that we consider is complete basis images. So, in that case what we will have is the reconstructed image u hat will be given by double summation say v k l into a star k l m n. Now, suppose L will vary from 0 to q minus 1 and say k will vary from 0 to p minus 1. So, instead of considering both k and L varying from 0 to n minus 1, I am considering only q number of coefficients along L and p number of coefficients along k. So, the number of coefficients that I am considering for reconstructing the image or for inverse transformation is p into q instead of n square. So, this p into q is using this p into q number of coefficients, I get the reconstructed image u hat. So, obviously, this u hat is not the exact image, it is an approximate image, because I did not consider all the coefficient values, and the sum of squared error in this will be given by epsilon square equal to u m n, that is the original image, minus u hat m n, which is the approximate reconstructed image, square of this, and you take the summation over m n varying from 0 to n minus 1. And it can be shown that this error will be minimized if our set of basis images, that is a k l m n, this is complete. Now, another point that is to be noted here, if you compute the amount of computation that is involved, you find that if n square is the image size, the number of computations or amount of computations that will be needed both for forward transformation and for inverse transformation will be of order n to the power 4. So, for doing this we have to incur tremendous amount of computation. So, one of the problem is how to reduce this computational requirement when we go for inverse transformation or whenever we go for forward transformation. So, we will continue with the discussion of this unitary transformations in our next class. Now, today let us consider the solution of the quiz questions that we had given at the end of lecture 9. So, remember that at the end of lecture 9 or during lecture 9 we were discussing about image interpolation and image resampling, and one of the applications of this we have said that if I scale an image or scale up an image, or if I rotate an image, or if I want to correct an image, there will be many cases where the information will not be available at regular grid points. So, interpolation and resampling aims to fill up those grid points where no information is available in the transformed image. So, here we have given a problem where this image will be expanded by 3. So, for solving this particular problem, if I consider this particular part, the same will be applicable for the entire part. So, if I expand this or if I scale it up by a factor 3, you will find that I will get a value 3 here, then for 2 subsequent locations there will not be any information. I will also have a 3 here. Here again for 2 subsequent locations there will be no information, I will have a 3 here. Here again for 2 subsequent locations I will not have any information. Here I will not have any information. Here I will not have any information. Here I will have the value 5. Now, the purpose is I have to fill up all these blank spaces. Now, we find that if I go for the nearest neighbor interpolation, the nearest neighbor interpolation says that you fill up this location with the value of the pixel which is nearest to it. So, if I go for that nearest neighbor interpolation, this location will be filled up by 3, 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 this 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 will also be filled up by 3, this will be filled up by 3, whereas these 3 locations will be filled up by value 5. So, this is what we have in case of nearest neighbor interpolation. If I go for bilinear B spline interpolation, then what I have to do is, when I want to fill up these blank locations, so here I had the value of 3, here I had the value 5. So, whenever I want to fill up this particular blank location, I have to take a linear combination of this pixel and this pixel. This will get an weightage of the distance of this pixel from this particular point, and a weightage of this pixel, the weight is given by distance of this pixel from this particular point. So, you will find that this particular point will be filled up by a value which is equal to 0.7 times 3 plus 0.3 times 3, which in this particular case is also equal to 3. But when I come to this particular pixel, the value that will be assigned to this particular pixel will be equal to 0.3 times 5 plus 0.7 times 3. Sorry, it is the reverse. This is 0.7 times 5 plus 0.3 times 3. So, if I compute this, I can find out what will be the value at this particular location. So, using similar procedure, I can find out what will be the values at all the points where I do not have any information in the transformed image. So, using similar procedure, you can find out the values at all the positions, all such blank positions where there is no value. The second one is also of same type. Here the image is to be rotated by 45 degree, and here again after rotating the image by 45 degree, you will find that there are some locations where there is no intensity value. So, for those locations, what you have to do is you have to go for inverse geometric transformation, and then you find that to which particular point in the original image this point lies, and you have to interpolate the value at that particular point using either bilinear transformation as is given in this problem, following the bilinear interpolation that we have discussed, and the value that you get there, you replace that in the corresponding location in the transformed image. So, following this similar procedure, you can also find out what will be the rotated image, rotated interpolated image. Now, coming to today's questions. So, there are some quiz questions on today's lecture. First one is, what is meant by a set of orthogonal functions? What is the difference between orthogonality and orthonormality? The third problem, determine if the following set of vectors is orthogonal or not. The vectors are 1 0 0, 0 1 0 and 0 0